In this last video, we'll go through this example on Duffing's equation, which is taken from our OER textbook. Let's just kind of look through that just briefly here. Again, this is a harmonic oscillator which adds on another forcing term. So we're used to these three terms being in some of the harmonic oscillators we've investigated in our homework and such, but this additional term incorporates gravity into the swaying motion of the crane they talk about in the textbook. Alright, now converting that from a second order equation to a first order system gives us this nonlinear autonomous system of differential equations. And what I want to do is investigate that in Maple. We're going to create some of the same graphs that we see here, so eventually we'll show this picture of the direction field, right, which is a picture of the phase plane with the direction arrows on it. Alright, so we're going to see what we can do here with Euler's method. Now, I'm not going to do the same exact initial value problem that I have there. So the initial value problem I want to look at is this one, where when t equals 0, the initial value for x is 0 and the initial value for v is 1. Alright, just one note about the difference between the notation that they're using here. They're calling just x to be the position and v to be the velocity, where in some of the other examples we've used y to be the position. So we might have had dy dt equals v. Alright, and then dv dt was in terms of y and v. They have it in terms of x and v, so I'm just going to leave it that way. Alright, I'm going to approximate over this interval from 0 to 25, and the step size we're going to use here is 0.025. Alright, this system is quite sensitive to changes in the step size and changes in the initial condition, as we'll see shortly. The first thing we want to note, though, in contrast to the last example we did, where we had a partially decoupled system, which we could actually write out the solution on paper, and Maple could certainly easily solve it for us. Here I've typed in this exact initial value problem into Maple. Now watch what happens when we execute it. Nothing happens. Maple does not solve this system. Maple cannot solve that system exactly. That nonlinearity that coming from that x cubed terms that comes in there, this is not a decoupled or partially decoupled system. It's a fully nonlinear system of differential equations. Very difficult to solve. The only quantitative information we're going to be able to get from this is by approximating it using Euler's method. Alright, now this is the same document which I will have posted in in Blackboard. This is the same document that I had the first example in, so I've already got the Euler procedure loaded in the document, but I got to define a new right-hand side function. I'm calling it F2 and G2, which are the right-hand sides of our differential equation there. Okay, so once we define them, I'm going to define a new function. This time I'm calling it capital G instead of capital E, which sends a t value through the procedure. So inside of there we have to change this to F2 and G2, change our initial time. Well, our initial time is still 0. Our initial x in this case is 0. Our initial v is 1. Our step size is 0.025. Alright, and there's our function capital G. Alright, now I've also, just for simplicity's sake here, I've defined the component functions right after that. Alright, so I'm calling it xg and yg, which gives us the first and second component. We're thinking about that as the x and the y component. Probably should have used v maybe here to be more explicit, but again, we think about the first component and second component a lot of times being x and y. Right, we could change that to vg if you want to. But anyways, let's just compare what it looks like when I plug in, say, a t value to the original function we called capital G versus what we've defined to be xg and yg. Notice they give us the second two give us the first and second components respectively. So if I want to plot it in the phase plane, we have to use the function capital G. If we want to do the individual components, we have to either use xg or yg. Alright, now what I've plotted here in Q1, and keep in mind, in contrast to the last video where we went through an example where we could actually write out the exact solution, all we can graph here is the approximate solution. Maple won't solve it for us. We can't solve it. This is the best we can do as far as graphing is concerned. Is here I'm plotting the solution in the with t on the horizontal here. All right, so we're plugging in these t values into our x approximate. All right, now why did I go up to 1,000 here? Our step size, remember, is 0.025. If we're going to go from 0 to 25 in steps of 0.025, it's going to take 1,000 steps. All right, think about taking that interval from 0 to 25 and breaking it up into pieces of size 0.025. If you do that on a calculator, 0.025, let's do it right here. Take 25 and divide it by 0.025, you're going to get exactly 1,000. Okay, so it's 1,000 steps. All right, there's the x approximate. There is the y approximate. All right, so I've called them Q1 and Q2 because what I wanted to do was make a graph similar to one I saw in the textbook where it had both the x component functions and the y components. So the x components in blue, the y components in red there. All right, I'm just going to flip back over to the textbook briefly because that is done in figure 2.36. They have the x component and the y component graphed in, or they're calling it x and v, really. I should say x and v in my Maple file. Notice though that the initial condition they're using is not the same as the one I had. They did 0 for x, which is the same, but they did y to be 1.7652. And then they also make a comment that in the next graph, and now notice, where did they get this graph from? Using a numerical algorithm. Well, they used something like Euler's method, or maybe something more sophisticated to come up with that graph. They changed the initial condition in the next figure to 1.7653, just the 2 went to a 3, and you get dramatically different looking approximate solutions. All right, so this is showing that this system is very sensitive to changes in the initial conditions, all right, especially to the initial velocities. All right, and that makes decent sense in terms of the swaying of the crane, the velocities corresponding to the wind. That's there. All right, so now let's go back to our Maple file. All right, and I'm going to do a little bit more with this example. All right, and what I want to do is I want to plot the direction field. All right, so I've called that Q4. All right, and I've got Q5, which is the plot of the approximate solution in the phase plane. All right, so let's look at the difference between the green graph that I have here and the blue and red ones before. These ones were the x and the y components respectively in blue and red. Notice we see some oscillation kind of happening there. X is going up and down between, you know, -1 something and -1 something. Y is between a little bit less than -1 to 1 there. And that's what we're seeing in this graph. We're seeing a spiraling motion in the phase plane. All right, so notice we plotted these as an ordered pair. The ordered pair, I chose to do xg and yg. We could have just done capital G by itself and it would have spit out the ordered pair. That would have been an alternate way to do this problem. All right, so that's one way to do it. Let me just do it the other way just to show you the difference. All right, so I'm just going to copy this down below, paste it, and let me just, I'm not going to bother giving it a name, but let me just show you the difference. So in here, instead of plotting these inside the sequence, instead of actually doing an ordered pair with the x approximate and the y approximate, we could have just done G of capital G of 0.025 times K. Because what does G spit out? G spits out an ordered pair. So this is going to give me the same exact graph as I had before. It's taking a little bit of time for that to evaluate because we're talking about doing 1,000 steps. All right, so we're sending 1,000 steps, whether we do it with the functions we've defined to be xg and yg for the first and second components, or the original approximation capital G. It takes a little bit of work for Maple to do that. All right, now I've got our approximate solution plotted in the direction field as well. We can see it's following those arrows pretty decently. Okay, now the last thing I want to just point out to you is, and we're going to find the equilibrium solutions using Maple in just a moment. There is an equilibrium solution. You can kind of tell it's spiraling towards that in the phase plane. It seems like there's something going on over here, right? Over near 4, and also over near -4. Right? There's kind of a clustering of these arrows. Sometimes they're pointing left and right and down, and it seems like there might be another equilibrium solution over there. So the next graph I'm just showing you is using DE plot and using the option of putting in multiple ordered triples. This list of ordered triples, which starts here, all right, each one of them's got 3. Each ordered triple there has a t, an x, and a y. I just chose the first component t to be 0 each time, and then the x and the y have changed. Now I've put 4 of them in there. I did 0, 1, I did 0, 2, and then I did ones that were close to the examples from the textbook, 1.76 and 1.77. Those were really similar to the ones. And then I chose the line color. I just wanted them to come out to be different colors. So red is the first one, blue is the second one. Let's compare those two. So red's basically, that's the same one that we did using Euler's method. All right, D-plot, unless we specifically tell it to use Euler's method, it will use something more sophisticated like the Runge-Kutta method. All right, now the other one, the next one, starting at 0, 2, that's the one in blue, it's going up, looks like to the right. We'll expand that in a minute. What's pretty interesting is looking at the difference between the 1.76 and the 1.77, which I've colored in green and purple respectively. The 1.76 is the one in green. That sort of goes towards this equilibrium point, which we'll talk about in a second, and then it starts to spiral in towards the origin. The other one sort of goes there and then bounces away. All right, so again, really sensitive to those initial conditions. All right, now, just to explore that a little bit, you can actually solve a system. Now, to find the equilibrium points of this system, we would take each right-hand side function and set it equal 0. So that's what I've done here. I've used these curly brackets. Those are set brackets, so the order doesn't matter. We're solving that system of two equations, two unknowns for these two variables, x and v, and we get these three ordered pairs solution. Well, if I would have ordered them, I could have got x first, then y second, or then v second. So 0, 0, 3.870, negative 3.870. So really these are backwards. They're not really listed as ordered pairs. I can fix that here by putting, instead of the set brackets, we can put, or instead of the curly brackets, the set brackets, we can put a close bracket along each side, and then when I execute that line, we'll see we've got x first, v second. All right. Well, if you do this by on paper, you're going to come up with the square root of 15 and plus or minus the square root of 15, which is about 3.87. So we're seeing that up here. There is an equilibrium point, equilibrium solution, constant solution along the x-axis. There's 3 of them, in fact. There's one at the square root of 15, 0, 0, 0, and one over at negative the square root of 15, 0. Now, what I want to point out here, I want to do one more thing, is I went from negative 5 to 5 for x and negative 3 to 3 for v. Well, let's increase the x. So what if I change that from going from negative 5 to 15 and then re-execute that line to redraw the graph? Now we can really see what's going on there. Well, those solutions that go to the right, they bounce up, and they bounce up very, very quickly. All right. If you try to do Euler's method with 1.76 or 1.77, and if you don't use a really small step size, the numbers are going to get really, really large, really, really fast. Okay, so that's just a good illustration of how nonlinearities in systems play, or for nonlinear systems and equilibrium points, how complicated the situation can be and how much the dependence on the initial condition could affect things.